Good morning, everyone. Myself Subhrangshu Sekhar Jana, and today I'm going to teach about the chapter of class 12th, chemical kinetics. Chemical kinetics is most important chapter. Chemical kinetics. Okay, it is an important chapter one. Before starting, whenever I teach in the class, also I used to explain the names of the topic. So if you got to know a general idea about that topic from the name itself, it will be so helpful for us. So here the important term which need to be explained, the term is kinetics. Okay, in class 12th, so in class 11th, we have heard about, they have studied about the chapter thermodynamics, and this today we're studying about chemical kinetics. So what is the difference between thermodynamics, and why did I mention about the chapter name thermodynamics? So it is because thermodynamics, what does thermodynamics do? So if I have to tell you that thermodynamics tells about the feasibility of a reaction. Thermodynamics tells us about the feasibility of a reaction. What do you mean by feasibility of a reaction? Feasibility of the reaction means the possibility of a reaction to happen. That known as feasibility of the reaction. And what we are going to study in the chapter of kinetics? Kinetics will tells us about the path. That path which should be efficient for us. Okay, let us understand this with an example from a classroom environment. Let us consider there is a classroom. Okay, and here is one student sitting. Let's suppose this is student A, and here imagine this is student B. Okay, now if I have to transfer the pen, let's say here A wants to give the pen to B. Okay, A wants to give the pen to B. Okay, so this is the feasibility, that the is there possibility that A can give pen to B? Yes. So this is the feasibility of the reaction. Now, by which path the pen should be given to B? There are numerous paths. I will consider three paths. One is the straight path, path 1. Another may be like this path 2, this path 3. So by seeing the picture itself, you can say that the path 1 would be feasible. Path 1 would be feasible. Why path 1 is feasible? Because this path 1 is the shortest distance, and you can complete the task with a minimum time. So what I mentioned here, the path 1, we should write it. I am writing everything. Okay, from the path, why we choose path 1? Because the path 1, it is the shortest distance and minimum time. That means I can say this path 1 transaction will be so fast. So this term fast term related to velocity or speed, but that speed term we generally do not use in the chapter of chemistry. So we will be using the chemistry language. So that would be corresponding terms will be rate. So rate is nothing but the kind of speed. So generally, what do we know about the speed formula? Speed equal to distance by time. This is speed. But here we are not going to discuss about speed. Okay, this and all we will study all in physics and all. So leave that part aside. So here today we will be discussing the chemical change with respect to the time. Okay, if I've changed the time, what does the change has been happened to the chemical species? So we'll be studying that. So if I've changed, if I have to take that change with respect to time, I'll be called that as rate. I'll be called that as rate. So I'll erase everything and I'll explain the rate and all with a count of 1, 2, 3. Okay, I'm going to erase this one, all these things. Okay, so now we're going to study rate. So what we discussed about rate. So here in the chemistry we're not going to transfer any pain and all. So now let's consider general reaction proceeding from A to B. Not B, leave it. Take it as A giving rise to product P. So now if I, let's say time equal to 0, time equal to t minute. So if I allow some time, then in the time gap some reaction will occur. Okay, that reaction occur means at the 0 time, in the initial time, the concentration of A should be A naught, initial. So that will be full. So if I allow some time, then what will happen? That amount of A will go for decomposition. That some amount of A will decompose, and that decomposed product, that decomposed reactant will be converted into product with the period of time. Okay. So I can write that how do we then define the rate? So rate can be defined as by simple formula that change in concentration of change in concentration of write it just general one, change in concentration by change in time. Yeah, but sometimes we may write generally write time taken. Okay, but many of you may ask, many of you may say that how does this concentration change if we take, we generally took that in amounts. No, if we're going to reactions, so first of all take some amounts. So the amount we deal in respect to moles. So now if I take only moles, then if I take the some and I have dissolved in that moles in some solvent amount, particular amount of solvent, then I will be getting some solution. That particular solution will have some concentration. That's why I have written change in concentration by change in time. And one more thing to remember, in this chapter chemical kinetics, we are not going to vary the volume, because if you vary the volume, then there will be change in the concentration. Okay, so keep in mind that the volume is kept constant in this chapter. Okay, we will take the variation in volume also, but here only we are going to discuss all the based on here whatever we are going to discuss, all will be based on a constant volume. That means the volume is not increasing, volume is constant. Okay, now go to know that rate is change in concentration by change in time. Okay. So now in the kinetics chapter, rate defined of two ways, two types of rate generally we define in the chapter of kinetics. So first one, rate, we generally define through differential rate and rate law. I'm going to next page, I will be explaining this one. Okay, so now first of all we need to write differential rate law. Differential rate law. So differential rate law means, 1 minute. Differential rate law. So now let us consider a general reaction in such a way that A of A, B of B giving rise to some C of C, D of D, where the small a, small b, small c and small d all are known as coefficients of the reactant A and B and product C and D respectively. Okay, now just to take in the first case t equal to 0 minute, not minute, we'll take in second. Okay, let's say t equal to 0 second, no reaction will be happen, everything will, no product has formed also, so everything will be the reactant. Now I have allowed some time to happen the reactions, let's say some t second. At t seconds in the start case, let's say this amount of a naught, this is b naught, 0 0. Now at time t, maybe the reactant, the amount of the concentration left, amount left for a is at and for b is bt. So here some has formed also ct and dt. So now how do you define the rate? How to define the rate? Just remember, we mentioned that in the previous case, that how do you define the rate? Rate is defined as change in concentration by time. And one more thing to remember, just keep in always mind that rate is always positive. Rate is always positive. Okay, so if I write to differential, rate, then how can I write? Okay, so I will write straightly. So for the differential rate, it can be written as just one thing. How to write? So just take the point. First point, take just 3 points you must follow. Then it will be easy for you. Nothing. Take the reciprocal of the coefficient. Okay, and put negative sign for the reactant. Put negative sign for the reactant. Put negative sign for the reactant. So these two, will you remember these only simple to for the important things. So if you remember these 2 points, it will be easy, so easy for you to write the differential rate law. Okay, so now we'll be writing. So what I've mentioned here, we have to take the reciprocal of the coefficient, and if it's reactant, then we have to put negative sign. That's it. We'll take reciprocal. So in general way, how I can write here, 1 minute, in the next one I'll be discussing this one. Okay, so okay, nice, thank you. So I'll minimize it to a little extent. 1 minute. Okay, it's good. Now we can write as the differential rate law. First we have to take the reciprocal of the coefficient. Okay, 1 by a. Now differentiation will take change in concentration of a divided by change in time. Okay, now check this. A is the a is a reactant or product. So a is itself a reactant, so simply we will write negative. Like that I can write minus 1 by b db by dt equal to 1 by c dc by dt 1 by d of dt by dt. Okay, now each term explain the rate of reaction. Each term known as a rate of reaction. Here one thing to remember, that I'll explain the downside here. Okay, see, here I have written 1 by a dA by dt. I'll take another color. It is known as rate of reaction. Now some people may think that earlier I mentioned that rate of reaction is always positive, but here a negative sign is there. How this could be positive? Okay, see, this A is in reactant. A is a reactant. So if you calculate the change means the final minus initial, so this change is also negative. So if I put another negative, that means it becomes positive. So hence proved it is nothing wrong that rate is always positive, keep in mind. Okay, so hence proved that rate is positive, a is decreasing and negative sign, negative positive. Okay, I think it is clear now. So one more thing, so if I'm writing this one, not, I'll take the color. Okay, if I write dA by dt, so this will be known as rate of decomposition of A. Similarly for BC, for B also rate of decomposition of B also can be written, and for C rate of formation of C, and for D rate of formation of D also can be written. So with this and based on this we can we can work out some numerical also. So with this we will now move towards a rate law. This now moves. So one more thing I think one more thing I need to mention here. I want to mention here one more thing. Sorry. One minute, just a minute. I need to clear this one. Delete. Just a minute. I will delete this one then. Okay. So one more case. One more thing I want to explain here. That is, anyone have you know about the extent of reaction? So extent of reaction generally mentioned here. Extent of reaction. Extent of reaction means, from the name itself, it is easy to know that what do you mean by extent of reaction. But actually, in the previous case, we've discussed about the rate and all. But how that rate law came, the differential rate law came, it actually came from extent of reaction. Extent of reaction. Let's say I'm taking one simple example. N2 plus 3H2 gives rise to 2NH3. 2NH3, na? So initially, there will be some moles have been taken. Moles have been, I'll take a general reaction, not this one. I'll take a general reaction, then I'll explain this two also. Let's say C. So initial the moles of A. Initial there would be a moles of A. Let's say N0, here also N0, here also N0. But at this time equal to 0. Time equal to if t second. N of A, N of B, N of C. Now how do we write the small a, small b, small c? How do we write the extent of reaction? So extent of reaction is nothing but it's the ratio of change in moles by coefficient. So formula I can write delta of n by coefficient. We generally represented by this way, zeta. Okay, so this is your coefficient and this is your extent of reaction. Extent of reaction. Okay. Okay, so now how to write the extent of reaction for the above reaction? We will be write delta n of A by, since it is negative, we will put this one, delta n of B by negative B, delta n of C by C. That only one sign convention always there. One sign convention will always be there, that for reactant you have to put the negative sign, and for the product you have to put positive sign, and that's it. So with this we will move towards the rate law. Okay, with this we move towards rate law. Extent of reaction I think now is clear to you. So now we'll move towards rate law. How do we write the rate law actually? Okay, 1 minute. Rate law. Rate law defined as, let's say there are A and B is going to product P, let's say here X and Y. So the rate law actually defined as rate law actually depends on the concentration of reactant. Okay, rate law concentration of reactant. Generally, first at the first case when this developed by, I think the rate law defined by maybe Van 't Hoff. Okay, I need to check one. The rate law may be defined by Van 't Hoff. This rate law actually first was explained for that only elementary reaction. Rate law explained for elementary reaction. So for elementary reaction we can write rate equal to K. Let's say this A and say B. The power will be alpha and beta. Here if you take the alpha, what is the alpha? What is alpha here? Partial order of A. Beta is partial order of B. If I take alpha plus beta, that known as overall order for the reaction. So now what if someone asks that what is the order of the reaction, you can simply say that it is the summation of the powers of the rate law. The rate law. And keep in mind that the order of the reaction is experimental. Order of the reaction cannot be found some the theoretical way. It is the experimental phenomena. Okay, so based on the order there are types of reaction also. So based on there are types of reaction. Generally we study zero order, first order and second order, third order reactions are so complex in nature, but in the only class 12th it is only up to there zero order and first order. So with that I'm going to discuss about that zero order. This I'm going to erase now. Okay, so let's discuss about the zero order reaction. Zero order reaction. So what does the rate law tells about us? That the rate is proportional to reactant concentration of the reactant. So now if it is zero means that order is zero. Okay, I can write like that. So if I have to remove that proportionality proportionality, I have to put some constant. This is k to the power 0. Now if any substance is the power 0, that will be taken as 1. So simply I can rate is rate equal to k. Here the rate constant is equal to k. So now we're going to derive that one. Let's say A giving rise to product P. Now we know that how to write the differential rate law for this A. So if it is in reactant means it is going to consume. So I can write this one d of A by dt as a rate. So now I have to put this one, this dA by dt equal to K of A. K of A. So that means 0. So now it is dA by minus of k dt. Minus of k dt. Since it is 0 in nature, it will become a, since the A has power at 0, so it will become 1. So we will be left with dA and minus of k dt. Now if I take the integration on both sides, okay, and I have to put limit time equal to 0, the concentration should be a naught. At time equal to t, the concentration is at. So integration of dA is a at minus k will be constant, it will come outside, dt integration t 0 time. So by solving this one we will be getting a t minus a naught minus equal to kt, implies that a naught minus a t equal to kt. Here this a naught corresponds to initial concentration of reactant time t, it means concentration of reactant at time t. Okay, so this is the integrated rate law. Based on this reaction, we can draw some graphs also. If you go to this one, so many things are there to explain here from the zero order, first order. And the zero order is out of any order of reaction, only zero order is the only reaction. Zero order is the only reaction which go for completion, except that no any order of reaction goes for 100% completion. Okay. So since it is on goes to 100% completion, the unitary method only be applicable on zero order method. What do you mean by unitary method? How to use that one? Okay, so I will be erasing this one. I will erase everything and go to next explanation. Okay, how to use that unitary method? It is so easy. Let's say one question is there for a zero order reaction. If the T50 is your 100 second, calculate T75. Calculate T75. One thing to remember here, that's the subscript 50 or subscript 75. That signifies that, let's say if it is written T50%, that means 50% of the reactant has been consumed. If it is 75%, means 75% of the reactant has been consumed. So if 75% reactant has been consumed, we will be left with 25%. We will be left with 25%. Okay. One more thing, I think I missed to explain, missed to say in the previous slide. Okay, first of all I will say that. Okay, now this half life. So integrated rate law, we got it is A naught minus AT equal to KT. What do you mean half life? Half life means the time at which half life means the time at which the initial concentration of reactant becomes half. Okay, so that means AT will become equal to AT by 2 at T half life. So now this equation 1 will become A naught minus A naught by 2 equal to KT, implies that it will become A naught by 2 equal to KT. Here will be T half, so T half will be written as A naught by 2K. A naught by 2K. So based on that we can try it out. So if T half is given to us, it is as 100 seconds. So with this I can calculate from here K equal to A naught by 2 into T half. It will be A naught by 2 into 100, A naught by 200. Now T75 means T 75% has been completed. We will be left with 25%. So I have to put in the reaction. The reaction I can write A naught minus 0.25 A naught equal to KT. It will be become 0.75 A naught equal to KT. Okay, 0.75 A naught equal to K. In place of K I can write A naught by 200 into T. A naught and will be cancelled. It will be time equal to 150 second. So time equal to 150 second. So this is the by formula I have done this. We have done by formula I have worked out this. Now by with the help of unitary method we are going to calculate. Okay. Remember, unitary method only works in the zero order reaction. So by unitary method I can write it as let's say for t 50% it is 100 second. T 1 for completion of 1% it will be how much? 100 by 2 second, sorry, 100 by 50 it will be 2 second. For t 75%, 75 into 2, 150 second. So this is done by Unidad method, and that one previously we did done with by the formula. So now we can draw a simple graph for this one. That graph generally asks for the zero direction. What is the expression this one now? A naught minus at equal to kt. Now if they ask draw a graph versus at and t graph, I'll erase those things then. Right. Okay, let's draw a graph. A naught minus at equal to kt. Draw the graph. It is at versus t. Okay, so we know that at versus t, so we have to convert like that. It should become at equals to a naught minus kt. Simply now this is the form of y. This is y, this is x, m and c. So now the graph will become like this. At here t and a slope of the graph one minute. Okay, like this is the graph. Here this is the intercept, slope equal to minus k, intercept equal to a naught. So this is all about the zero order reaction, and thank you everyone. So this is we've discussed for that. I have recorded this one for the demo class, and for this I have discussed about that initial of kinetics, chemical kinetics, what is the rate and how to define the rate law, differential rate law, what is rate of formation, and what is order, how to determine the order of the reaction, and based on the types of order, first I have discussed about that zero order reaction. So thank you.